If you are a student of periodic table, if you are required to study the periodic table in your courses, then this is perhaps the most important class which would help you understand the periodic table thoroughly and completely. See, the idea behind this class is that what we'll do is that we'll look at this periodic table, which I'm sure you are very familiar with now. If you have subscribed to doorsteptutor.com, our course there, or if you have been a subscriber of this channel, then this periodic table is something that you will be very familiar with. But what we'll do today is we'll try to understand how the electrons getting filled in the various shells, subshells and orbitals relate to this periodic table. So as we add more and more, one more electron, how does the electronic configuration change? And based on that electronic configuration, the new electronic configuration, how that new element gets its place on the periodic table. So that is what we will be studying today. So the first thing that we'll do is that we'll start with hydrogen. Now hydrogen, because we are adding the very first electron, it is going in the first shell. The first shell, the lowest subshell is of course S. So in the S subshell of the first shell, hydrogen gets its first electron, and that is the electronic configuration for hydrogen. It's 1s1. That is how we denote it. So 1 in the superscript means that how many electrons actually went to S subshell of the first shell. What about helium? So helium, you will say, sir, very simple. It is just the 1s subshell would get 2 electrons, which is correct. Now what about the next ones? As we come to lithium, the first shell has completely filled up. Okay, so there is no more room in the first shell. So where would the next electron go? It has to go in the second shell, and second shell also has the basically it also has an S subshell. The very first, the lowest energy subshell of the second shell is also S. So in the case of lithium, it has an electronic configuration of everything that is there in helium plus 2s1. That is how we denote the electronic configuration. We use the helium's configuration, the last noble gas that we encountered, and on that top of that noble gas we say that it has one more electron, lithium, and that one more electron has gone to the 2s subshell, the S subshell of the second shell, that it has one extra electron. What about beryllium? Beryllium has full electronic configuration of helium, and plus it has 2 electrons in the 2s subshell. Now after this, the 2s subshell is completely filled up. There it can hold a maximum of 2 electrons. So the next electron, where would it go? It would go to the 2p subshell. Okay, so because the second shell has 2 subshells, S and P. The S subshell has a single orbital, the S orbital of course. The P subshell, it has 3 orbitals, Px, Py and Pz, and of course we have studied this in detail in our classes. So the P subshell has 3 orbitals, Px, Py and Pz. Each of those 3 orbitals can hold a maximum of 2 electrons, electrons of opposite spins, and because of that a total of 6 electrons can come in the 2p, the 2p subshells. Okay, so 2p subshell can get a maximum of 6 electrons. So we'll go from 1 to 6, and as we add more and more electrons to this 2p subshell, we go from boron to carbon to nitrogen, oxygen, fluorine, and finally we come to neon. So neon has the electronic configuration of helium, and plus it has a full second shell which has 2s which is completely full and a 2p which is completely full. Okay, so that is the electronic configuration of neon. So with this we have filled up the second period. Okay, so these are the periods as we go from top to bottom. As we move from left to right, these are the groups. Okay, so the second period has completely we have filled it, and we have reached the electronic configuration of neon, which has helium, which is 1s2 and then 2s2 2p6. That is the configuration for neon. Now if I add one more electron to this neon, you will know where it will go. So you already know that it will go to the 3s. Okay, so after 2p6, what comes? 3s. It is the third s orbital, the s subshell of the third shell. So it is 3s. So what is the electronic configuration for sodium? It is neon, and on top of neon I also have one more electron which goes in the 3s subshell. So magnesium, it will be neon and then 3s2. Okay, so this is 3s2, and after this we have aluminium, in which we will start filling the 3p orbitals. So after 3s orbitals, 3p orbitals would come. So 3p orbitals will go from filling up from aluminium, which is 3p1, till argon, which is 3p6. So what is the electronic configuration of argon? Argon is full neon, and on top of neon we have the third shell. Now we have filled the s and p orbitals, and we have reached argon. Okay, so this is the electronic configuration for argon. Now of course there is some problem here. There is something that I am missing, and some students have already, they might have guessed it. So we start from the top. Okay, so what do we have at the very first? We have 1s2, then we have 2s2, 2p6, and then in the third shell I have 3s2, 3p6, but additionally I also have 3d10. Okay, so that is the problem. There is another subshell in the third shell, which is the d subshell, and it has a total of 5 orbitals, again giving me a total of 10 electrons which need to be filled here. But the thing is that because d orbitals are so far away, even though the argon, it has the d orbitals are not filled up yet, it is very stable. It does not try to easily fill up those d orbitals. Okay, because these d orbitals are very high in energy, they are very far away from the nucleus, and so argon becomes a noble gas, even though the d orbitals of the third shell are not filled up yet. They have not even started filling. Okay, this is first reason. The second reason is that we end the period at argon. The second reason is that now for potassium, the next electron will not go to this 3d10 orbital, but where would it go? It will go to the 4s2, 4p6, 4d10. It will go to this 4s orbital. So in the case of potassium, if I add one more electron to argon, I will not fill up the 3d orbitals. I am not taking them here, that one more electron in the case of potassium. Okay, so let's go to potassium. So potassium is argon, and I have one more electron, but that electron is not going to 3d orbitals, but where is it going? It is going to the s orbitals. And why is that the case? We have studied this in detail. It is because of the shielding effect. Okay, so the shielding effect and effective nuclear charge, those two concepts are very important. The lower shells have a greater shielding effect on the d orbitals of higher shells than the s orbitals. So because of this, the 3d shell, the 3d orbitals are more effectively shielded by the electrons in the lower shells, okay, then the corresponding 4s. So 4s becomes lower in energy. It is, although the principal quantum number is 4, it is further out. It's more outside, more further away from the 3d orbitals, more outside the atom. Even though 4s is further outside, the principal quantum number is higher, it is still lower in energy because it is less shielded as when compared to the 3d orbitals. Okay, so because of that, the next electrons come in the 4s orbital. Okay, and similarly for the calcium also the same thing happens. The 4s2, it's argon 4s2, the next electron occupies the s orbital, the 4s orbital. After 4s orbital, then we will start filling the 3d. Okay, so if you want to understand how the order of filling of orbital happens, it happens like this. So first thing gets filled like this, then 2s filled gets like this, then 2p6, 3s2 like this. Okay, then 3p6, 4s2 like this, and after 4s2 it is 3d10 and then 4p6. That is how the orbitals are getting filled. So always remember this diagram. Okay, after 4p6, okay, so after 3d10 we will then fill the 4p6. So it is not the 4s orbitals and then 4p orbitals. No, that is not the case. 4s, then 3d, then we go back to the third shell, we fill its d orbitals, and then we fill the 4p orbitals. Now because the 3d orbitals are coming in between the two two fourth shell orbitals, okay, the 4s and 4p, because these things are coming in the middle, these things are, or we are filling up the d orbitals here. That is why they are known as the transition elements, okay, because they are in transition. We are in transition. We are suddenly started between the two 4 orbitals, 4 subshell. We have suddenly started filling the third shell again, okay. So that is why these are known as transition metals, okay. So all of them, this is here in the case of from scandium to zinc, these 10 elements, we are filling the 3d10 orbitals. And once this 3d10 orbitals, all of this they are completely filled in zinc. Till zinc we have completely filled the 3d subshell. Once it is completely become full, then we go to the gallium. Now in the case of gallium, we are started filling the 4p shell, okay. So gallium is 3d10, 4s2 and then 4p1. And then germanium will do the next thing. We'll start the next electron will go to 4p, okay. So on and so forth until we reach krypton. In the case of krypton, we have argon. So what would be the structure of krypton? So let's just write that. It will be argon, and then of course the 3d10. So the d electrons are completely full, and then we have 4s2 and then 4p6. Now in the case of fourth orbital, the fourth shell, okay, in the case of fourth shell, we have 4d10 and we also have 4f14. There are also f orbitals coming into play here, but this 4f14 and 3d10 4d10 we completely ignore. As soon as the s and p orbitals of the fourth shell they become full, we completely ignore the d and f orbitals. So even though no electrons have been filled yet in the 4d orbitals and 4f orbitals, even then the krypton is stable because s and p orbitals are completely full. Because again the same reason, the 4d and the 4f orbitals, they are very so far away from the nucleus that krypton is very stable, even though those orbitals there are no electrons in it. Krypton does not readily try to add electrons to those orbitals, and it is still a noble gas, okay. So with this we have reached the krypton. And then the next, in the case of the next period also, the fifth period, we will be filling up the fifth shell. So it will start from 5s. So this is the 5s will get filled here, and then the 4d, remember the 4d has not yet filled, so 4d orbital will get filled till we reach the cadmium. So cadmium 4d orbital will get filled, and then the 5p orbital will from indium onwards, the 5p orbital will get filled, and will reach the xenon, okay. Now remember, we have not yet filled the 4f orbital at all. So 4f orbital has not even come into picture yet. We have not yet filled it, okay. So after the fifth period, the sixth period comes, and here we are filling the 6s, and then 6s gets filled till barium, and from here in the next one, the lanthanum, that is where we will start filling the 4f orbital. So those are known as lanthanides, and they are actually put at the bottom of our periodic table right here, okay. So cerium is the first element which has the 4f, first electron gets in the 4f orbital, and that starts with cerium. So cerium gets the first electron in the 4f orbital right here. So it is 4f1, and from cerium onwards till we reach the lutetium right here, okay, we are filling up the f orbital, and these are known as the lanthanides. Now there is an entire chemistry associated with lanthanides, which we will study in another class. Okay, once the f orbital is filled, now we go back to our filling of our d orbital. So lanthanum gets the first electron in the d orbital, it is 3d1, and then we go back to our d orbitals. Sorry, not 3d, okay, it is the 5d, okay. So lanthanum gets the electron in the 5d orbital, 5d1, and then hafnium 5d2, and so on and so forth. The 5d orbital is what we are filling now, okay, and then we reach the mercury. Mercury has the 5d10 the d orbital, the 5d shell is completely filled. Okay, and then we go to thallium and so on until we reach radon, where we are filling the 6p shell. Okay, and that is the 6th period. Okay, the same thing happens in the case of the last period, the 7th period, which starts from francium. Okay, so we start by the s orbital itself, which is the 7s. Okay, so 7s will get filled up here, and then in the middle we still have to fill the 5f. Okay, so the 5f orbitals are getting filled up, which is right here in the middle. Okay, and these are known as actinides. Okay, so we have a complete 14 elements in the actinide series, in which we are filling up the 5f orbitals. Okay, so those are also put here at the bottom. So, and then we go back to filling up of our 6d orbitals. Okay, 6d orbitals start filling from actinium so onwards. Okay, the 6d orbitals are getting filled up, and then we fill our p orbitals, which starts from here till here. So this is the p orbitals getting filled up. Which p orbitals? Of course, we are in the 7th period, so it is 7 p orbitals which are getting filled up, and we reached our last element, which is 118. Okay, so that is how the periodic table gets filled up, and that is how we understand how we get our lanthanides and actinides at the bottom, in which the f orbitals are filling. These are known as the f block elements. In the middle, I told you already, from here to here, these are the d block elements, all of these, because the d orbitals are getting filled up in this region. Okay, so these are all the d block elements, and in this region our p block is getting filled up. Okay, right here. So these are known as the p block elements, and here these two right here, they are known as the s block elements, because our s orbitals are getting filled up. So very, very simply, we were able to understand in its entirety how the filling of the periodic table works. What you should remember is this chart. Okay, how the electron filling actually happens. The chart that we have drawn up on the left hand side, this chart is actually very, very important. Okay, so hopefully things are very, very clear now. This is very important class. Listen to it again and again. Take a periodic table with you, study it in detail, try to fill up the electronic configurations as you go along compared to what we have here in this class, and understand it very well, because this will be very useful in our future classes, where we will discuss the valencies of various elements, especially the transition elements. The d block elements, the few of the d block elements, the transition metals, they have multiple valencies. So if you know how the periodic table is getting filled up, then it will be very easy for you to understand the multiple valencies of the transition elements at that point. Okay, thank you very much.